Hello, curious minds, picture this. Two black holes, each one more powerful than you can imagine, spiraling toward each other, destined for a cataclysmic collision. But before they can merge, they face a strange barrier. What stops them from coming together, and how do they overcome it? Before we start, if you're new to black holes or need a refresher on what makes these cosmic giants tick, be sure to check out our suggested videos. Now let's dive in. Now, to understand this phenomenon, we first need to know how these black holes can even get close enough to each other in the first place. After all, black holes, despite their reputation as solitary creatures lurking in the darkness, are not immune to the allure of gravity. The first way black holes can come together is through stellar evolution. Massive stars, when they reach the end of their lives, go through supernovae. If two massive stars are part of a binary system, they might both collapse into black holes, and as their gravitational forces draw them closer, they can become locked in orbit around one another. In this case, the star's explosive deaths mark the beginning of a black hole partnership. But what happens if black holes aren't part of a binary system to begin with? Well, gravitational capture can step in. In the dense heart of galaxies where gravity is much stronger, black holes are more likely to encounter each other. If one black hole drifts close enough to another, the gravitational forces between them can pull them together, forming a new binary system. Star clusters, especially dense globular clusters, provide another fertile ground for black hole interactions. In these regions, black holes are not only formed through stellar evolution, but also through violent encounters. A black hole might collide with a star or another black hole, and the interactions could result in one of these cosmic giants being pulled into orbit with another. As these black holes interact, they can eventually form binary systems, locked in a tight gravitational dance. The closer they get, the more their orbits shrink, making their eventual merger inevitable. And then, there are the galactic mergers. When entire galaxies collide, the central supermassive black holes are disturbed, causing them to move closer to one another. This is yet another way that black holes can form a binary system. Now let's explore what happens when these black holes are so close they can't resist any longer, and what stands in their way. When two black holes get close enough, their gravitational forces pull them into a dance of death. But before they can merge in a cataclysmic collision, they face a challenge: the Final Parsec Problem. The parsec is a unit of distance used by astronomers, roughly 3.26 light-years. The Final Parsec Problem refers to a mysterious bottleneck that occurs when the black holes are about 1 parsec apart. At this distance, their gravitational radiation is not enough to bring them closer quickly. It's as if they hit a wall, leaving scientists wondering, how do these black holes overcome this final hurdle to merge? At this stage, the energy loss from gravitational waves is no longer sufficient to shrink their orbit quickly. Without additional forces or interactions, the two black holes could remain stuck in this final parsec for billions of years, delaying or even preventing their merger. One potential solution lies in the chaotic environment surrounding the black holes. In galaxies with dense star clusters or gas, these objects can interact with the black holes, providing the additional energy or momentum needed to push them closer. Stars passing near the black holes can be flung away, transferring energy and momentum in a process called dynamical friction. Another possibility involves the arrival of a third black hole. If galaxies merge multiple times, their central black holes can form complex, chaotic systems. The gravitational interactions between 3 or more black holes can destabilize the system, eventually driving the original pair closer together. There's also the influence of the universe's gravitational wave background. This background may nudge the black holes closer, providing the final push needed to overcome the parsec barrier. In some cases, the black holes may be surrounded by an accretion disk. The friction within this disk can rob the black holes of angular momentum, allowing them to spiral closer together and bypass the bottleneck. Now, a new study by scientists in Canada has proposed another fascinating solution: dark matter, specifically a type called self-interacting dark matter, or CDM. Dark matter, the mysterious substance that makes up most of the universe's mass, is usually thought to be invisible and non-interacting. But self-interacting dark matter could change the game. Unlike regular dark matter, CDM particles interact with each other via an unknown force, creating a drag force that can transfer energy away from the black holes. This extra friction helps them close the gap. The researchers found that these interactions must be finely balanced. Too much, and the dark matter becomes too diffuse; too little, and the friction is ineffective. Their findings also match gravitational wave data, offering a new way to explore dark matter and black hole physics. With the Final Parsec Problem solved, the two black holes are finally free to collide. But what happens in those final moments? Let's explore the epic conclusion of this cosmic journey: the black hole merger. After overcoming the challenges of the Final Parsec Problem, the two black holes enter their final moments. This merge is a maelstrom of unimaginable energy. These titans are now locked in a final, fatal embrace. Their immense gravitational pull draws them inexorably closer, and in these last moments the most powerful forces in the universe are at play, reshaping the very fabric of space-time. As the two black holes draw closer, their gravitational fields become increasingly distorted, like a funhouse mirror reflecting their impending doom. This distortion is not just a visual spectacle, it is a profound alteration of space-time itself, a testament to the immense forces at play. The fabric of space-time itself is stretched and squeezed, releasing a torrent of energy in the form of gravitational waves. These waves ripple outwards, traveling at the speed of light, carrying with them the story of this cataclysmic event. Think of it as the universe's way of communicating the sheer scale of the forces involved. They traverse the vast expanses of space, reaching distant corners of the universe, where they can be detected by advanced instruments on Earth, providing us with invaluable insights into these violent events. These signals can be detected by observatories like LIGO and Virgo. Finally, in a blinding flash of energy, their event horizons touch, and the two black holes collide, merging into a single, more massive black hole. This moment is both an end and a beginning, as the newly formed black hole settles into its new state, having consumed its partner in a final act of cosmic cannibalism. This newly formed behemoth, still reeling from the encounter, vibrates like a struck bell, sending out its own unique set of gravitational waves. These vibrations are the black hole's way of adjusting to its new form, a process that can take millions of years. These ripples in space-time, faint yet persistent, are the echoes of a cosmic dance billions of years in the making, carrying whispers of the universe's most violent events. They remind us of the dynamic and ever-changing nature of the cosmos, where even the most massive and seemingly eternal objects are subject to the forces of change and destruction. Strangely, the newly merged black hole has a mass that's less than the combined masses of the original pair. For instance, when LIGO detected its first gravitational wave event in 2016, a 36 solar mass black hole merged with a 30 solar mass black hole, creating one of just 63 solar masses. What happened to the missing 3 solar masses? Well, they were converted into energy in the form of gravitational waves. In fact, about 5% of the total mass in every black hole merger gets converted into these waves. For perspective, that's like transforming 3 suns entirely into pure power, released in mere seconds. An event so powerful it outshines all the stars in the universe combined, yet occurs in complete, utter silence and darkness. And that's how two black holes come together in one of the most powerful events in the universe. But the mysteries don't end here. What else do you think we can learn from black hole mergers? Could they hold the key to even deeper cosmic secrets? Let us know in the comments below. If you enjoyed this adventure, don't forget to like, subscribe and ring the bell so you never miss out on more space exploration. Thanks for watching. Until next time, keep looking up.